Hello everyone, good morning, good afternoon. Welcome to this webinar hosted by Waterfall Dynamics. My name is Joanne from RFD's Aberdeen office. Thank you very much for joining us today. Today we are bringing you a case study webinar from the tNavigator user community. I am pleased to introduce our guest speaker, Mehdi El Fadouzi, Senior Reservoir Engineer from ADNOC Group. Mehdi's project, Integrated Economic Optimisation for Optimum Waterflood and Hydraulic Fracturing Performance, investigates how tNavigator handles the challenges associated with waterflood optimisation, including well spacing, well length and well stimulation. He will share his work carried out in using tNavigator's assisted history matching and uncertainty functions and the workflows used to achieve optimal values for the mentioned parameters. I would also like to introduce my colleagues joining us today, Maxim Kizavanov and Evgeny Guzarov, who work closely with the team at ADNOC, providing technical support for their projects. Due to a large number of attendees, everyone has been automatically muted, so if you would like to ask a question, please type it into the chat box and we will answer as many as we can at the end. Maxim and Jenny will be helping us with the Q&A, so hopefully we can answer your question, whether it's specific to this project or just a general tNavigator inquiry. If we don't have time to address your question live, we will follow up with you on email afterwards. And if you have any further questions, just feel free to contact us on asktnav@rfdwn.com and somebody will get in touch with you. So I'd like to thank Mehdi and his colleagues at ADNOC for helping us to make this webinar happen. And I will now hand over to you to begin the presentation.
Okay, so thank you, Joanne, for the introduction. My name is Mehdi, and we're going to explore in this case study how to find the optimum waterflood and fracture design from an economic standpoint. So this workflow is quite general. However, it gives you a bit of, just to give you a bit of context, this study was done for a very large onshore green reservoir, and the thickness of the reservoir and the poor reservoir properties are basically gang up and make the development quite challenging. So we're going to see how we can optimize, how we can maximize the economic value for such a field. Optimizing a waterflood development boils down basically to answering three questions. What is the optimum well spacing? What is the optimum drain length? And what is the best stimulation technique? And the answer to these questions is not always obvious, because doing more sometimes results in less value. So for example, reducing well spacing is well suited for a tight formation. However, the drawback is more drilling expenditure to cover the aerial extent of the field. At the same time, make it too large and suddenly you have a lack of pressure support and a bunch of inactive wells. So similarly, it is possible to drill longer drains to enhance the PI injectivity index and also reduce the well count. However, longer wells require more rig time, more completion material, so they come with a higher price tag. And another pitfall is the risk of bypassed oil when you drill very long wells. And finally, in terms of stimulation, placing additional fractures along the well is definitely going to boost up the productivity index and injectivity index if also placed in injectors. It also allows you to inject more and hence faster the recovery. The cons of that is that you got an overall increase in completion cost, and if the fracture spacing is too low, you can end up with production interference between the fractures. So a nice way to say it is, as Don Walcott said in his applied waterflood book, is the optimum well spacing is the one achieving the maximum investment efficiency with the fewest number of wells that facilitates the sweep out of the reservoir within the shortest amount of time. And by rearranging the Darcy law, we can get this convenient formula that gives the maximum technical well spacing to inject a certain pore volume PVI within a certain time frame T. And you can observe from this formula that the well spacing is both a function of reservoir properties, so things we have really no impact on, and engineering slash operational practice. So we see, for example, that doubling the dimensionless productivity could reduce the well count by a factor of 2. So hence the focus on stimulation, which comes as a fraction of cost of drilling a well. You can also see in the numerator delta P which is the pressure lost between injector and producer. And that indicates that the operator should keep delta P near technical potential to maximize benefits. So for example, practically speaking, we're talking about injecting at as close as possible to frac pressure and produce at the minimum safe bottom hole flowing pressure. And the plot on the right is showing a typical well spacing for a vertical well as a function of formation permeability, considering two scenarios. The dark gray one is the one for unstimulated, and the light gray is for stimulated well. And you can see for a 1 millidarcy rock, the well spacing is around 200 meters for unstimulated, and around 400 up to 700 meters for a stimulated well. So it is quite useful as a ballpark figure. However, simulation is required to refine this figure for horizontal wells, knowing that every 100 meter spacing is equivalent to 20% well count. So reducing by 100 meters your well spacing, or increasing your well spacing by 100 meters would reduce your well count by 20%. So it's really important to get an accurate figure. So now that we went through the problem statement, we will go sequentially through the mechanistic model setup, the fracture design, the economic model, and the NPV optimization. So first of all, it's really important to set up the mechanistic model with just enough detail to ensure it captures the right physics within a reasonable runtime. So in our case, the model was built with a resolution of 30 by 30 meters on the horizontal plane and 1 feet resolution vertically, resulting in 500,000 cells and allowing for at least 20 cells between injector and producer, which is very reasonable. The vertical heterogeneity is an important aspect of this reservoir, and that's the reason behind the choice, our choice to go down to 1 feet vertical resolution. And the properties were populated based on a core data calibrated to PTA, and the average permeability is around 1.5 millidarcy. But we'll see later on a different case with the higher permeability. So it's important also to set up the production controls correctly to ensure proper reservoir management. So the way it's set up here is the injector are under BHP control set at frac pressure, while the producer in the middle is controlled by reservoir voidage. So whatever gets injected, the volume injected by these two wells is going to be the rate at which the producer is going to produce. So let's go through the fracture design in numerical models. The choice we've made here is to select 5 important variables that we want to optimize. The first one is D, the distance between injector and producer. And the range we've chosen for that variable is 300 meters all the way up to 800 meters. Another important variable is the length of the drain. So in our case, we are comfortable draining 8,000 feet horizontal section all the way up to 15,000 feet, which is the upper limit for our drilling fleet. And in terms of a last variable that we want to optimize is the fracture density, which is defined as the number of stages per 1,000 feet. And we basically chose anything between no stimulation all the way up to 4 stages per 1,000 feet. And what we want to know is what is the optimum number to maximize the economic value of this reservoir. And as you know, the data file allows you to define these variables. So it's quite useful. You can define the range that you want to select. And also you can calculate variables for well placement. So for example, we've set up a certain distance between injector producer, and this variable is going to impact the placement of the well in the grid. And these variables are calculated. So we're going to calculate the landing point and the TD for injector and producer this way. And also another set of calculated variables is the number of stages. So we've set up as a variable the fracture density. However, if we want the number of stages, we have to calculate, it will depend on the length we've selected for the well. So this is another calculated variable. There are many methods available to model fractures in a numerical model, and each method has its pros and cons. So this table summarizes their limitations in terms of difficulty to implement, introduction of negative connection factor, constraints on well/fracture geometry, constraints on grid orientation. So some methods are only available if your grid is oriented along the maximum horizontal stress, the early time accuracy, and finally, the elliptical drainage shape. And for example, if the easiest method to model fractures is the equivalent wellbore radius / negative skin. So it's a method where the user simply changes the wellbore in the completion data deck to a larger wellbore, or introduces a negative skin to mimic the same productivity index. So these, the wellbore radius is typically defined based on a relationship between wellbore radius, equivalent wellbore radius, and dimensionless fracture conductivity. So relationships such as the Cinco-Ley relationship is quite useful in that matter. And but the issue with this method is it can introduce negative connections if the fracture goes beyond the Piesman radius. It can, it's very constraining in terms of well and fracture geometry. It has to be a vertical well. The fracture has to be vertical also. It's constraining in terms of early time accuracy, because for a tight reservoir within the first few months, this method is not accurate at all. And finally, it cannot capture elliptical drainage shape. And then you got ever increasing methods with a different set of complexity. So you can you have the effective permeability method, the pseudo well connection, whereby you introduce pseudo connections between the well and grid blocks which are in the fracture plane. You've got the LGR method, the nested LGR method, which is the method that we're going to present in this webinar, and finally the unconventional fracture method model, which is basically a full physics modeling of fractures. It's very time consuming. It's well suited for a single well model, but as long as if you go to a multi well, it's quite painful to implement. So the way fracture design is implemented is in tNavigator is you get to define your fracture path, which is the azimuth of your fracture, and the way it's done in our implementation is that the landing point, which is calculated and is used to define where is the first fracture. Next is you have to define the fracture template, which is the geometry of your fracture plane. In our implementation, we've chosen a single fracture geometry, which is given by the fracture engineer. However, there could be other implementation where you want to optimize the fracture geometry itself. So you may go for longer fractures, thicker fractures, and you have to see which one is the most makes the most economic sense. And finally, you've got the fracture stage. So it's a very nice feature where you can define the first MD of your first stage all the way up to the last stage, and you can define the number of stages you want. So in our implementation, as we've said before, the number of stages is a calculated variable that depends on the length of the well and depends on the fracture density, X stages per 1,000 feet. So what the user has to choose then is the level of accuracy. So it is a nested LGR method, and you have to decide on how many nested LGR you want to go for. So it can go from a level 1 all the way to a level 6. And we've made comparisons to look at different levels. Here, the plot on the left-hand side shows streamlines between two different levels of nested LGR. And on the right-hand side, you can see the level of detail that you can go for from level 1 all the way to level 6. So how do we choose the grid level, the right grid level? When explicitly modeling numerical fractures, the trade-off has to be found between the result accuracy and the speed of calculation. So the plot on the left-hand side shows on a monthly basis the liquid rate production for the producer, and you can see the different LGR method, the different grid levels don't line up exactly. You've got different levels of accuracy. So what you want to go for is to do a cross plot of FOPT versus CPU time, and to see what is the right grid level to give me exactly the same, exactly the same cumulative oil, but with less computation time. What we found is a grid level of 3 is quite good. It's we get an FOPT within 1% accuracy, which is satisfactory for a high-level assessment, and we managed to get down the CPU time by 40%. So if you want to do hundreds of simulations, it's really it's very important to make sure the CPU time is as low as possible. So let's move on to the economic model. What typically people do is they've got an Excel-based economic model where they copy-paste profiles and get economic KPI. And what we've done here is we migrated this economic model to Python, which is a very easy way. It's a very convenient way to calculate KPI, economic KPI on the fly. So you don't have to copy-paste profiles. You can just generate within the workflow. You can generate your cash flow. You can generate your NPV. You can calculate your ROI, etc. So it's very useful. And the way the economic model was set up is it allowed a fair comparison between the different developments that were proposed. For example, longer wells have additional drilling cost because of rig time and material. So for longer wells, we have a certain cost, X million per 1,000 feet. And also fracturing, going for a 10-stage fracturing or a 20-stage fracturing has a different cost. So we included within the economic model the cost of fracturing per stage. And what you end up with is a waterfall where the Python script that we set up can calculate the revenue, it can calculate the DRILAX, and the different OPEX. So it's really detailed model where you account for liquid processing, gas processing, water injection, and well maintenance. And finally, when the well dies, you've got a certain abandonment cost, and you end up with the net revenue. And the Python script is basically doing this calculation while accounting for the parameters that we define. So, for example, your well length for producer LP and your well length for injector LI are going to impact the cost of extending the lateral. Also, the fracture density times well length is going to give you the total number of stages, and that will impact your fracture stage cost. And the NPV, as a second step, the NPV is calculated by summing up the discounted cash flow. This is an NPV at pattern level. But what about if you want to upscale what you observe at pattern level to a field level? So the field that we're considering here has hundreds of kilometers square, so it's quite wide. And you've got to multiply your NPV by the number of patterns. And the number of patterns is simply a function of the reservoir area, the length of your wells, and the distance between injector and producer. That's how the model was set up. So how the optimization was done is we've used the PSO optimization and we defined NPV as a variable to maximize. And you can see that within roughly 180 runs, the PSO converges to an optimum NPV. What is very interesting here is that you've got a 5 times fold of increase between the worst and the best NPV. So it really means that we need this kind of optimization brings a lot of money. It brings a lot of value, and it's important to get as close as possible to the optimum NPV. Also, why did we set up a sector model to run this kind of calculation? We could have taken the full field model and created different cases with different well length, different distance, but compare, for example, the runtime for a single sector model run, which is around 30 minutes in our case, using 4 nodes. Compare that to tens of hours for a full field model with 48 nodes. It's really, the difference is drastic. This kind of optimization cannot be done at the full field model level. And also, if you look at the how much time was needed to do the whole optimization, we're talking about half a day, 12 hours. It's really fast, and it allows you to optimize on different assumptions. So here we have the 1.5 millidarcy rock. We'll see in the next 2 slides what happens when you go from 1.5 to 5 millidarcy. So here is the overall histogram of the outcome. So you can see here the interwell distance highlighted in blue are the top NPV case. So you can see the range that we've selected was 200 meters all the way to 800 meters interwell distance, but the optimum NPV is obtained when you go for 500 meters. Also, in terms of well length, you can see for producer, which is the top plot, you optimize NPV by going for 12,000 feet horizontal, whereas for injector, the optimization goes to 15,000 feet. So what it really means is that drilling, once you reach this 15,000 feet limit for your injector, drilling a longer producer is not worth it. Why? Because it cannot be supported by the line injectors. Drilling a longer producer would just mean spending more drillex with no additional revenue. And also in terms of fracture density, you can see that the optimization is advising us to go for 1 stage per 1,000 feet. So now let's look at the case with 5 millidarcy. You can see the histogram moved a little bit, it shuffles. And if we compare both cases here, you can see when you get to a higher permeability, your optimization advises you to go for longer, larger well spacing. So you go from 500 to 600 meters well spacing. Also, the optimization is quite logical in the sense that it advises you to drill a longer producer. So now your injectors within the 5 millidarcy rock are able to inject a much bigger volume. And it is, in that situation, it is worth drilling a longer producer. And what I would like to discuss here is the difference between optimizing NPV at sector level versus optimizing at field level. So what I want to say, an important message here is that optimizing at pattern level is not a guarantee that you optimize at field level. The reason for that is because sometimes drilling more suboptimal patterns can outstrip drilling less optimum patterns. So basically what it means is you can end up with the pattern NPV advising for making a decision to go for a longer well, because that allows you to reduce the number of, because that allows you to maximize the NPV. However, at field level, maybe the optimum is to go for a shorter well, because in that that will allow you to place more patterns and generate more revenue per pattern. And we see that difference when we do a cross plot of NPV sector versus NPV field. The case of optimizing NPV at sector level is the one on the extreme right, and the one optimizing NPV field is the one at the top, the one at the top, the star at the top. And you see here that there is a clear difference in terms of outcome, especially in terms of length of the producer and in terms of fracture density. The difference is that the pattern level is a 12,000 feet horizontal well for the producer, but the field pattern is the field optimization is basically, it's an 8,000 feet producer. Also, the number of stages, the pattern is optimum with the 1 stage per 1,000 feet, whereas the field is optimum with 3 stages per 1,000 feet. So you can see here, that's the reason why it's important to differentiate between both. So NPV is quite useful to understand the cash flow, but another very important parameter here is the ROI also, because NPV is does not give the full picture. The ROI is defined as the ratio between profit and cost of investment. It's a measure of profitability of your development, although it lacks the time factor that we have in the NPV. But it's important to have both NPV and ROI, because the ROI tells you based on how efficient are you in generating revenue out of a certain capex. And it's a very good metric when you want to compare different development scenarios, but also to compare different developments within your portfolio. Let's say you've got I can develop reservoir A or reservoir B. In that sense, it makes sense to compare the ROI for both developments. So from an investment point of view, you want to maximize both NPV and ROI. And here, in this case that we looked at, you can see the NPV versus ROI scatter plot is quite wide. So it means that we can end up with a good NPV, but the ROI will be completely different in both cases. And we see a difference in terms of length of producer and in terms of fracture density for the injectors. If you want to maximize NPV, you would go for a shorter producer. But if you want to maximize ROI, you have to go for longer producer. Why? Because having a longer producers means you have to drill less, so your capex is reduced. And if your capex is reduced and you maintain profit almost at the same level, your ROI is maximized. So it's important to compare both, and it's advised for any type of FDP to include both metrics. So the takeaway from this session is there is a big value in using mechanistic models to understand the behavior and to run fast sensitivities, as long as it captures the right physics. So in our case, what is the right physics? It's vertical heterogeneity. In your case, it could be capture the horizontal heterogeneity. So in this case, the horizontal variogram was larger than the interwell distance, so it didn't make sense to include it. However, there could be other cases where you want to include both. Another takeaway from this session is that maximizing economics is a multifaceted exercise. You've got to look at NPV. You've got to look at NPV at different levels, at sector level, at field level. You've got to look at ROI also to make it attractive. And we've uncovered here some advanced tNav capabilities. We've talked about the flexible simulation of multi-stage fracturing, introducing Python coding for economics, and optimizing NPV using PSO. And other ideas that we can take from this presentation is that you can get faster economic evaluation of FDPs. So instead of waiting for a feedback loop where you hand over the profile to an economist, and then you probably have to hand over less than 10 profiles, less than 10 proposed FDPs. In this case, you can run hundreds of FDPs, and you can get a fair idea about the economic value of these FDPs before handing over to the economist. Another idea is to define the best fracture design. So typically, fracture engineers are are using different metrics to design the fractures. They term to focus on short-term fold of increase kind of metric, where you look at what is the stabilized flow with and without fractures. Whereas what we're looking here at is the long-term NPV value, which is really what investors are looking for. And finally, it can guide commercial discussion with service providers. So here we've included the cost of stimulating the wells. And we can have a sensitivity where we can compare different prices. At a certain price, we see that the NPV is maximized if we proceed with hydraulic fractures. And it can basically allow you to have a better discussion, a better idea about what to go for in terms of contract. So this will end my presentation and open the floor for Q&A. However, before that, I'd like to take a moment to thank my colleagues, Faisal and Nabila. And I would like also to thank the tNav support team, Maxime and Evgeny. They've been really proactive and great to work with. And I would like to thank the organizers of this webinar, Joanne and Alexandra. So that's it from my side, and the floor is open for Q&A. Thank you.
Thank you, Mehdi, for the presentation. I'll just share my screen again. So we have a few questions coming in, so I'll just start reading those in a minute. And if you do have any questions, you can just type them into the chat screen. And we do have quite a few, so we might not manage to get around to them all, but as I said earlier, we will send those out by email. And also just to let everyone know that RFD are going to be attending SPE ATCE at the Dubai World Trade Center later on this month. So if you are around, then please pop by our stand, which is number 735, and say hello. Okay, let's get started with some questions. Mehdi, most of them seem to be for you, so if Jenny and Maxim have gotten off lightly this time. How far have the nested LGRs been extended in the grid in vertical direction?
There was no need to extend them in the vertical direction because the resolution was small enough. So we went for a 1 feet resolution vertically, and it was deemed sufficient. What really matters when you go for, in this case, we're talking about vertical fractures. What really matters is having enough LGR in the horizontal direction.
Okay. Could you consider a dual porosity, dual permeability model to simulate fractures, or is it the last line of your matrix of fracture simulation methods?
It is, yes, indeed. It is possible to use DP, dual porosity, dual permeability models for this kind of for modeling fractures, but it is less convenient. You'll have to do it manually, which is really time consuming. The reason we went for this kind of modeling is it's a matter of basically setting up the model is a matter of a few hours, and you can do a lot of sensitivities. Now let's look at a case where you have to do a dual porosity, dual permeability model with different stages. So you'll have to build a model for 2 stages. You'll have to build another model for 4 stages. If you change the well length, suddenly you have to define another model. It's doing each one manually. It's really time consuming. Here, everything is done automatically. So that's the reason we went for nested LGR.
Okay. Can you include the duration of injection in your optimization workflow?
Yes, it is possible. It's a good question. You can optimize. You can use the multiple object selection method in tNav, which allows you to optimize 2 or more variables. So it can be useful for that. And just to build on this question, you can see that there is value also. I mean, you propose the duration of injection. There is another thing which is really important when you go to offshore fields is the facilities limit. So you may want to optimize NPV, but at the same time remain within the facilities limits in terms of liquid production. And you can do that kind of optimization within tNav by setting up a multi-objective optimization.
Okay, let's maybe do 2 more questions and then we can wrap up today. Did you try different optimization algorithms? Do you see any differences?
No, we did not. We went for PSO because that's the default method. And since it's taking half a day, we did not see the value of investigating different options or even tweaking the PSO parameters. But if we were in a case where it was taking a few days to run, then definitely there is a value in trying different methods or even changing the inputs in a PSO.
Cool. And let's do one last question. Did you try vertical well with one fracture and compare with horizontal well with fracture? Was MPV your objective function or ROI? Sorry.
Okay, it's a good question. For this kind of reservoir, we did not try vertical wells because it's been done before. The results were not satisfactory. The reason for that is the thickness of the reservoir is too small. So if you go for vertical well, the PI is really low, and you'll have to place your injectors very close to producers. So it's been demonstrated with the field trials that vertical wells would not work, even fractured vertical wells, and automatically we wanted to optimize horizontal wells. That's the way we wanted to do it. And you can see we didn't go for short horizontal because it has been tried also. So we went for 8,000 all the way to 15,000 feet horizontals. And the second question was, do we want to optimize NPV or ROI? I think we need to optimize both because what the investors are looking at is what generates the maximum cash flow, what generates the maximum revenue, but also doesn't require me in borrowing a lot of money. So they have to look at both. And there is each company has a certain threshold in terms of ROI. So potentially what you can do is that cross plot, NPV versus ROI. You set up a minimum ROI expected by your investors, and you can select the maximum NPV within that cloud of scenarios.
Perfect. Thank you very much, everyone, for all the questions. As I said, there are quite a lot more, so we'll wrap up there. But I will send out all the questions over to Mehdi, and hopefully he will kindly answer them, and then we'll get the answers out to you. So thank you very much again, everyone, for joining the webinar, and of course thanks to Mehdi and ADNOC for sharing this case study with us. And we look forward to seeing you on the next webinar, and hopefully at ATCE. Thank you very much.
Thank you. Thank you for inviting me. Have a good day.
Thank you. Goodbye.
Bye-bye.